next speaker is Chirag, and he will talk about applications of Fermat's little theorem.
Good afternoon to everybody. My name is Chirag Kar. I'm a second year BSc math student at Fermat Institute of Eminence. I would like to take this opportunity to thank Corollaries for giving me this platform to talk about this very interesting subject that I've recently become interested in. Today, my talk is going to be on Fermat's little theorem, a very basic theorem in number theory, which has massive applications. So let's begin then. Let's dive straight into it. Now, let P be a prime number. Let A be in the set of integers such that GCD of A and P is 1. Then A to the P minus 1 is congruent to 1 modulo P. Now, of course, congruence over here just means that P divides A to the P minus 1 minus 1. So now we have the statement and we can verify with examples that this does hold true. So let's look at the proof. Now, how do we look at the proof? Here, we are going to give a very short, very quick proof, and it will give the listener an opportunity to verify exactly why our proof is actually correct. So let's take a look at the set of elements over here, which is A to A until P minus 1A. That is the first P minus 1 multiples of A. What happens over here? Now, each of these, we can see that does not give a zero remainder. What happens if it did? Well, let's see. Suppose RA is congruent to 0 mod P. Then we would basically have, because A and P GCD is 1, R is congruent to 0 mod P. But because R belongs to the set 1 to P minus 1, R has to be equal to 0 because it is strictly less than P. But that is a contradiction simply because it just does not belong to this set. Therefore, this never happens. Similarly, we always have distinct elements. We always have distinct remainders upon when we divide each of these elements with P. Why is that true? Let's see what happens if RA is equal to SA for some R and S in the set 1 to P minus 1. If that happens, again, similar argument over here. This argument being that because A and P GCD is 1, R is congruent to S, therefore R is equal to S. And therefore, both of them would essentially be the same element, regardless of whatever remainder they give. Therefore, what basically happens now is that we have P minus 1 distinct remainders, and they are all from 1 to P minus 1. Why is that? Because of the division algorithm. Therefore, each remainder occurs at least once. Now, suppose we multiply all of these together, consider this. Let's consider this. A, 2A, three A, 3A, until P minus 1A. Now, as I pointed out, each of the remainders from 1 to P minus 1 occurs at least once. So then all of these, all the remainders will occur. So this should be congruent to P minus 1 factorial mod P, right? But then what happens if that is the case? Now, the GCD of each of the elements over here from 1 to P minus 1 is 1 with P. So the GCD of the product is also 1 with P. Therefore, we can cancel the P minus 1 factorial over here by Euclid's lemma, of course. So this essentially turns out to be the very statement of the problem. Am I clear? Or is there, if there is any point which needs any justification, or if there are any questions, please feel free to interrupt me. Now, this was a very short, very quick proof of what Fermat's little theorem is. Now, here I'd like to direct your attention to a talk last year by Shantanu Ghosh, wherein she basically motivated the entire concept using the concept of counting necklaces, and she actually justified why a prime number is necessary, etc., and did a Beautiful, beautiful motivation of how we can essentially use Fermat's theorem to solve a very nice combinatorial problem. So I would recommend that everybody, if you wish to look at another treatment of this proof, then you can refer to VSSP 2021, a talk by Anthony Ghosh on Fermat's theorem. But today we are going to move forward and now start with the meat of the matter. Let us now look at a simple application of this theorem, which is a basic corollary. Now, suppose P is a prime number. Then for all integers A, we have that A to the P is congruent to A modulo P. Now, why is that true? Now, the question now essentially sort of rests upon, two cases. That is, suppose we pick some A, let A be in Z. What are the two possibilities for us? The two possibilities being either P divides A or P does not divide A. Correct? Now, okay, what happens if P divides A? In that case, we essentially have that P also divides A to the P, right? It's like multiplying A. Now, it divides P A to the P, it divides A. This then implies that P divides A to the P minus A. But this is equivalent to saying this by definition, it just means that A to the P is congruent to A mod P. Wonderful. Now, this statement is true for at least P divides A, but then what happens if P does not divide A? Well, if P does not divide A, what happens to the GCD of A and P exactly? Anybody can answer that if you'd like to.
1.
Excellent. Can you give me the reasoning? What are the possibilities for the GCD? It's either 1 or P, right? Because those are the only divisors of P. Now, because P does not divide A, it cannot be P. Therefore, it must be 1, which essentially tells us that we can apply our most prized possession, that is Fermat's little theorem. Now, by Fermat's little theorem, we have that A to the P minus 1 is congruent to 1 mod P. Wonderful. Now multiply A on both sides and we have our answer. This theorem, while being extremely simplistic and looking extremely simple, is actually very interesting because now we've proved that the above thing implies the below thing, but is the converse true? Do we have that if this is true for a prime number P, then do we have this, the above statement? The above statement over here. Let's check. Suppose, assume that the corollary that we just proved is true. Then A to the P is congruent to A for mod P for all integers A. Correct? Now, let P be a prime number. That we know in both cases it's a prime number. Now, if suppose that A and P, the GCD is 1, then we can just write A to the P is congruent to A. A to the P is congruent to A as A times A to the P minus 1, right? We can just do that. Now, if we can do all of that, essentially what we have is A times A to the P minus 1 is congruent to A times 1. Because A and P GCD is 1, we can cancel both of them out. We can divide by A and we get A to the P minus 1 is congruent to 1. Essentially, what is it that we've shown? We've shown an equivalent statement to Fermat's little theorem as I put it before. And so both of these statements are all right to be used as Fermat's little theorem. Does anybody have any questions to me? All right then. So moving on from that, now let us look at some interesting problems that we can actually tackle with this. Some applications of this theorem, which looks very simple, but is actually extremely powerful, as I'll show you in a few problems now. Now, let P be a prime number. Then for all AB in the integers, P divides AB to the P minus BA to the P. Now, why is this true? Is my question. Why would this happen? Now, let's suppose let A and B be in P. Let A and B be in Z. Now, by our corollary, we basically just have by our corollary, which I just write as for. By corollary, we just have that A to the P is congruent to A mod P. Similarly, B to the P is congruent to B mod P. Now, because of that, what happens to AB to the P, for example? Now, this is congruent to AB mod P. Similarly, BA to the P is congruent to BA mod P, which is the same as AB mod P. So, that difference essentially, AB to the P minus BA to the P is essentially congruent to 0 mod P. Thus, P divides it. Am I correct? All right. Now, here is another very interesting problem, which is that how can we compute the last digits of 3 to the 100? This seems to be like a staple problem in many Olympiads, etc. But now the question is, how do we actually compute something like this? Now, if anybody has any ideas, my first question to everyone is, what is it? We obviously need to compute this modulo some number. But then what number do you think we should compute this modulo? Anybody can answer this one.
Modulo 10.
Modulo 10. Excellent. But then we just proved something for prime numbers, right? Can we actually use Fermat's theorem directly? Can we actually do that? No, right? Because 10 is not prime. Yes. So basically, we have to work around. We can't admit defeat. So we have to work around something. So now let's try to see what can we do. 10 is basically 2 times 5, correct? That is the prime factorization of 10. Does everybody agree with this? You can say yes. Now, if 10 is equal to, yes. So let us look at, suppose what happens now, if you look at 3, say 3 square, not 3 square, actually. What is 3 mod 2? Of course, we don't need to apply Fermat's theorem, but then by Fermat's theorem also, 3 mod 2, 3 is 3 to the 1 is congruent to 1 mod 2. Similarly, 3 to the 4 is congruent to 1 mod 2, mod 5. Now, because of that, what happens? Now, because of the above congruence that we have, we essentially have this, right? That 3 to the 4 is also congruent to 1 mod 2. Because of the above congruence, we also have 3 to the 4 is also congruent to 1 mod 2. Correct? Now, because of this, we essentially have that 2 divides 3 to the 4 minus 1. 5 divides 3 to the 4 minus 1. What is the GCD of 2 and 5? 1, right? Now, we have from our experience with number theory a theorem wherein if A divides C and B divides C with A and B GCD is 1, then AB divides C, right? So then the product of these two has to divide 3 to the 4 minus 1. And so what we have essentially shown is that 3 to the 4 is congruent to 1 mod 10. But this essentially gives us the solution, right? Because 3 to the 100 is congruent to 3 to the 4 to the 25, which is just congruent to 1 mod 10. And the answer to our problem is essentially 1. Wonderful. All right. Again, anybody has any questions, please feel free to interrupt me at any point in time. All right. Another problem that I think I found interesting recently was this problem, which is about summation. It involves summation up till p minus 1 terms modulo p. What is the value of this? This very summation from 1 to p minus 1. Remember, p is a prime number. Now, do you know something about the GCD of a prime number and everything from 1 to p minus 1? What would be the GCD of each of these elements, of which we're taking the bars? Sorry?
1 each.
1, right? 1
Yeah.
for all of them. 1 is trivial, and it is true for every prime, because there is none of these are divisors, right? Other than 1, of course. None of these are divisors of p. So it's only 1 is the possible. 1 is the only possible GCD. Wonderful. Now, if each of them have GCD 1, then what are each of these powers congruent to exactly? Again, applying Fermat's little theorem. Each of these,
Each is
they're all,
congruent to one module.
yes, it will be congruent to 1, right? So the entire summation, essentially, now 2 to the p minus 1, etc., etc., all of the summations is congruent to 1 plus 1 plus, like p minus 1 terms. There's p minus 1 terms, right? Of course, for p. By Fermat's little theorem. Now there are p minus 1 terms. This is congruent to p minus 1 mod p. But this is the same as saying that this is the same as congruence to minus 1 mod p. And that essentially gives us a solution to our problem. Another very interesting application. Now, another related problem to the above one is, now we know what 1 to the p minus 1 being added, or like x to the p minus 1 being added from 1 through p minus 1 is. But then can we really say something about the pth powers? Can someone give me an idea about, okay, 1 to the p I can do, it's 1, I know that. Now, can you tell me what about 2 to the p? P is a prime number again.
We can use the corollary which we have proved.
Excellent, excellent. So if you can use a corollary, the corollary basically tells us that a to the p is congruent to a mod p, correct? Now, basically what happens afterwards is that we have 1 here. This is congruent to 1, this is congruent to 2, congruent to 3, 4, 5, up to p minus 1. So essentially this entire summation becomes congruent to the sum from 1 to p minus 1. Some of the first p minus 1 natural numbers. Of course, in all of these scenarios, please note that I haven't stated it, but p is an odd prime, because this problem becomes different for like p being 2, for example. So please note that. So now 1 plus 2 up till p minus 1 mod p. Now, what is this sum? What does this sum evaluate to exactly? This entire summation?
P into p minus 1 by 2.
Wonderful. We use the sum of the first n natural numbers, the formula, first things you prove by induction. We use this. It evaluates to this, right? Now, do you see why I stated that p is an odd prime? Because if p were even, this entire thing would not be, this would not be an integer, as an example, p minus 1 by 2 would not be an integer. So because p is an odd prime, p minus 1 is even. Therefore, p minus 1 by 2 is an integer, and therefore this entire expression is essentially a multiple of p. So this entire number is a multiple of p, and this thus is congruent to 0 mod p. Now, here is where this is one of the things. This is one of the more interesting applications. Now, this theorem, or like this statement that we are going to prove right now, is in itself might seem very arbitrary, but rather it is a statement which can be used to prove something extremely powerful. So, suppose that a is an integer, that p greater than 2 be a prime divisor of a square plus 1. Then p is of the form 4k plus 1. Remember, p is prime, it's a divisor of a square plus 1, and we want to show that it is of the form 4k plus 1. Now, how do we go about doing this? Let's start. Now, p is a prime divisor, right? And now, by the division algorithm, p is in the integers. So P has to be P has to have remainders either 0, 1, 2, 3. Now, can P have a remainder 0 with upon division by 4? Is that possible? Remember, P is a prime number. No, right? Because then P becomes a multiple of 4. Exactly. So P cannot have a remainder of 0. P cannot have a remainder of 2. Why is that? Because if suppose P had a remainder of 2, we could write P as 4k plus 2. But then this is just 2 times 2k plus 1. So then it's an even number. It cannot be prime, right? Unless, of course, we're taking P to be greater than 2 again. So it cannot be a prime number, right?
Yes.
So 4k plus 2 is also not possible. Therefore, the only possibilities for P is 4k plus 1 or 4k plus 3. Now, okay, one simple example of a prime divisor which is of the form 4k plus 1 would be, say, 5. That is one example. For 4k plus 3 is, of course, 7. That's another prime number. But now, how do we show that it has to be of the form 4k plus 1? I'm going to use the method that I learned first, the first time I actually tried to do this. Let's try contradiction. Now, suppose that P is not of the form 4k plus 1. What happens then? Then P has to be of the form 4k plus 3. In that scenario, what happens in that case? We have that P is a prime divisor of a square plus 3, a square plus 1. Now, because P divides a square plus 1, what happens to the GCD of P and A? Can it be P? It cannot, right? Because if GCD of P and A over P, then P would divide A. And if P divides A, then P divides A square. If P divides A square, then P divides A square plus 1 minus A square. Therefore, P divides 1. And that is a contradiction. Does that make sense, everyone?
Yes.
All right. All right. Now, because P and A, the GCD is 1, we can apply Fermat's little theorem. Then basically, what do we have? We have that A to the 4m plus 2, because, sorry, to the 4k plus 2 is congruent to 1. What P? Again, I'm using both the characterizations of P. However, we have that P is of the we have that P is a square that P is a divisor of, so a square is congruent to minus 1 mod P. So if we raise a to a square to the power of 2k plus 1, which is an odd power, what would happen on the right hand side? We're raising minus 1 to the same power, right? What would happen here? Would it be minus 1 or plus 1? It has to be one of the two. Minus 1, right? Minus 1 mod. But then, isn't this essentially just a to the 4k plus 2? So then, this number is both congruent to 1 mod p and congruent to minus 1 mod p, which is a contradiction. We have arrived at a contradiction. Since it is not possible, it follows that P has to be of the form 4k plus 1. Now, with this, this is one of our, now with this exact theorem, I'd like to leave as an exercise a very interesting application, which is, you can use this theorem essentially to show that primes of the form of the form 4n plus 1 are infinite. Or a better way to phrase it is, there are an infinite number of prime numbers which are of the form 4n plus 1. This can be used as a lemma to prove this very, very strong, very, very interesting statement. Now, with all these examples and with all these exercises, etc., I have a feeling that I've convinced all of you, hopefully, that This theorem is extremely powerful. But then we have not asked a very natural question as of yet. Yes, we have a theorem. We have an implication as a matter of fact. If we go back, we see that if it's a prime number, then such an implication holds true. Such a condition holds true. What is the natural question here? Does the converse hold? Do we have? Is the converse true? Now, you can probably check for a very long time for a lot of numbers, and you would feel that the converse is also true in many cases. But then the answer to that question is an emphatic no. Why is that? Well, you can thank Robert Carmichael for it. Consider the number 561. What happens here? Suppose we have 561 over here can be factored as 3 times 11 times 17. So clearly 561 is composite, right? Now, if this is the case, suppose there is some A such that the GCD of A with 561 is 1. If because of this, what happens? Do we have that GCD of A and 561 is 1? Do we have A and 3 is 1? I think we do. Why is that? Because what is the other possibility for the GCD is 3, right? But then 3 divides A. 3 divides A, 3 divides 561. So it's a common divisor of these two. So the GCD has to be at least 3. But that is not possible, right? So then the GCD of A and 3 has to be 1. And we can argue similarly to show that the GCD of A and 11 is also 1. And the GCD of A and 17 is also 1. Now, 561, now these things hold true. We of course have our trusty old friend Fermat's theorem, which basically helps us, which tells us from the first one that A square is congruent to 1 mod 3. A to the 10 is congruent to 1 mod 11. And similarly, A to the 16 is congruent to 1 mod 17. Wonderful. But we can write the above statements in a slightly different way, right? Now, what is A square to the 560 by 2 congruent to? Remember, 560 by 2 is what? It's 280, right? That is a natural number. We can raise A square to such a power. But this is 1, so this entire thing has to be congruent to 1 mod 3. Arguing similarly, what happens to A to the 10 to the 560 by 10? Modulo 10, of course. 560 by 10 is just 56, right? It's 1 mod 10. Again, similar argument. And arguing similarly, we can also show this. That this is congruent to 1 mod 16. Now, this is a very similar argument, right? This is the same as saying that A to the 560 is congruent to 1 mod 3. And similarly, otherwise, of course. But what are the GCDs of all these, sorry, mod 17? What are the GCDs of all these 3 prime numbers? They're distinct primes. So it is always 1, right? So because these two, the GCD is 1, we have that A to the 560 is congruent to 1 mod 33. Similarly, A to and using that fact that A to the 560 is congruent to 1 mod 17, and that 17 does not divide 33, we finally have that A to the 560. I'll just write it out. We finally have that A to the 560 is congruent to 1 mod 560. What we have essentially shown is that if A and 561 has a GCD of 1, then A to the 561 minus 1 is congruent to 1 mod 561. So, yeah, congruent to 1 mod 561. We've shown this. But then this is the same as Fermat's, same as like the condition that we were looking for, right? Essentially, we've shown that there is an n, there is a composite n for which a to the n minus 1, a and n if GCD is 1, then a to the n minus 1 is congruent to 1 modulo n. But we were trying to find if n is prime. So essentially, we have a counterexample. These are what we call Carmichael numbers. I would like to end this talk by talking about two important things. Carmichael numbers. So first of all, what are some examples of Carmichael numbers? We have 561, we have 1105, and my personal favorite example, 1729. Why this is my favorite? I have a feeling you will know. With that, I would like to thank the organizers of this conference and bid you goodbye. Thank you very much.
Thank you, Chirag. That was a good presentation. Any questions anybody have? Okay, so I'll again thank all the speakers to give for their talks.